Hi guys. Hey, tomorrow in class you're going to be working on section 3.2, and it concerns a theorem. It's a little obscure. You just have to remember what it is and be able to work through the problems. It's the mean value theorem. And let me just give you a kind of a picture and show you what the mean value theorem is. So let's start with a picture of a graph. So first of all, you have to have a function that is continuous and differentiable. Something that looks maybe something like this, where you're going from some a value along the x-axis to some b value along the x-axis. If f of x is continuous and differentiable, then when you take the slope of the line between the two endpoints, whoops, it's supposed to be going through the two endpoints. Let's say that the slope here is equal to 1. As long as the black curve, f of x, the original curve, is continuous and differentiable, there will be a point somewhere between a and b, let's say right here, where the curve has slope that is exactly the same as the line that goes through the endpoints. And the mean value theorem guarantees that that point exists. We're going to call that point C. This really is what you're going to be trying to find. Now you're guaranteed to have at least one point. There may be several. But let's talk about the conditions of differentiability and continuity and why they're important to the mean value theorem. Let's say you have a curve that goes from, say, A to point B, and it's not differentiable. Something that looks maybe something like that. So it's not differentiable right at C. If I take the slope of the line between the two endpoints, there is no point in between A and B. You could say that this is the C value right here. However, you can not only draw a line that's parallel to the given line, but you can draw several lines, the rest of which are not parallel. So there is no value of C in that case. It must be differentiable. In the case of continuity, if I look at a similar graph, again, let's go from A over to B, and I have a graph that looks something like this. However, right here, say I have a discontinuity. When I find the slope of the line between the two endpoints, and I go to find my value of C, let's say that this should be C. The problem is I can't have a line tangent at that point because there is no point there. So it must be differentiable, and it must be continuous. Now I should mention one other thing. It must be differentiable on the open interval from A to B and continuous on the closed interval from A to B. So for continuity, it has to be continuous at every point between A and B and at the endpoints as well. For differentiability, it just has to be smooth between A and B. It does not have to be differentiable at the endpoints. Okay, so let's go ahead and work a problem, and I think you'll see how this works. So I'm going to use the mean value theorem to find C if f of x is equal to 5 minus 4 over x. And in this case, I'm going to go over the interval from 1 to 4. Okay, first of all, we need to check continuity from 1 to 4. And here's the way you're going to do it. you're going to look at the original function and ask yourself, where is f of x discontinuous? Well, there is a vertical asymptote at x equals 0. So the assumption is that that graph is continuous everywhere except at the value 0. Well, since 0 is not in the interval from 1 to 4, we can say that it is continuous. For differentiability, you use the same technique, except you use the derivative. So f prime of x is going to be equal to 5 derived to 0, and negative 4 over x, and speaking of which, I can think about this as being negative 4x to the negative first, so that I can avoid using the quotient rule. That drives to positive 4x to the negative 2, or 4 over x squared. So, is this differentiable from 1 to 4, not including the endpoints? Well, again, what I want to do is I want to think about now what this graph looks like, and I have a vertical asymptote on my derivative at x equals 0. But 0 does not fall from 1 to 4, so yes, it is differentiable. So since it's continuous from 1 to 4 and differentiable from 1 to 4, there exists a value of c between the endpoints where the original curve has slope that's equal to the secant point between the two endpoints. Okay, so here's how we're going to do it. First of all, I'm going to get rid of all this stuff. And now that I've proven differentiability and continuity, I'm going to go back to the original and begin to work the problem. On your paper, you'll keep all this work. So what I need to do now is I need to come up with the ordered pairs of the endpoints, with 1 being my first x value and 4 being my second. As you all know, the original function is the point machine. So if I plug 1 into there, I get 5 minus 4. That gives me 1. And if I plug 4 in there, I get 5 minus 1, which is 4. So my two endpoints are 4, 4, and 1, 1. To find the slope between them, I simply use my change in y over my change in x. And I get 3/3, or a slope of 1. And now, just like when you were finding equations of tangent lines, what I want to do is find where f of x has a slope of 1. How do I do that? I set my slope machine, which we already know, f prime of x is equal to 4 over x squared. I set that equal to the slope, and I solve. So if I cross multiply here, I get x squared is equal to 4. I square root both sides. I get x is equal to plus and minus 2. However, I'm only looking for the value of 2 between 1 and 4, so I can get rid of the negative. Positive 2 is my c value, and this is the value that you're looking for. All right, let's try one more here. If I have y is equal to x to the 2/3 minus 1, and I want to know if the mean value theorem applies from negative 8 to 8, just as normal, first of all, we have to find continuity. Is this thing continuous from negative 8 to 8, including the endpoints? Well, if I look at this function right here, there's nothing in the denominator, so I have no vertical asymptotes. I also have no holes. So, yes, this is continuous from negative 8 to 8. However, when I look at the derivative, my y prime is going to be equal to 2/3 x to the negative 1/3, which is the same as 2 over 3x to the positive 1/3. And I think about what this graph looks like. This gives me a vertical asymptote on my derivative at x equals 0, which means it is not differentiable at x equals 0. 0 is in the interval from -8 to 8, so the mean value theorem does not apply. All right, let's look at another one. How about f of x is equal to the square root of 2 minus x. Let's say I'm going from -7 to 2. As always, first I check continuity, going from -7 to 2, the endpoints, including the endpoints, and I look at my original curve here and I think about what values of x that could be. If I plug in -7, I get the square root of 9, which is 3. If I plug in 2, I get the square root of 0. And the domain of this curve goes from -infinity all the way to 2. Well, all those values are included in this interval here. So yes, it is continuous. There are no holes or vertical asymptotes. How about differentiability? Going from -7 to 2. Well, if I find the derivative f prime of x, and I derive 2 minus x to the 1/2, I have to use the chain rule. That's going to be 1/2, 2 minus x to the -1/2 times -1, which simplifies to 1 over 2 times the square root of 2 minus x. All right, now thinking about what that derivative looks like, what you'll notice here is in the denominator, x cannot be 2. That would give me 0 in the denominator. But remember, differentiability does not include 2. And every number in between -7 and 2 works in this derivative. So yes, it is differentiable. All right, guys, the next, this screen and the following one, it's just a little too quick, so I'm going to post it to another